Scientists have been working for centuries to understand time and space, offering various theories. However, renowned physicist Sir Roger Penrose recently shared a surprising discovery made possible by the James Webb Space Telescope. It challenges the conventional understanding of time. So what did the telescope reveal that led to Roger Penrose's claim? And how does this affect the scientific community, which has developed many theories based on time and space? In this video, we'll delve into why Sir Roger Penrose argues that time doesn't exist and the Big Bang wasn't the true beginning of the universe. Understanding the mysteries of time and space has long been a focus for scientists, cosmologists, and physicists. They've delved into the cosmos to uncover bits of the past that can shed light on the present. That's where advanced scientific tools like the James Webb Space Telescope come into play. This telescope, an upgrade from the Hubble Space Telescope, has been a cornerstone of the scientific community since its launch on Christmas Day 2021. The James Webb Space Telescope has revealed hidden aspects of space, like the most distant and ancient galaxies, which were previously concealed. Scientists believe that studying these ancient galaxies and interstellar objects can provide insights into the early universe and how time began. The telescope achieves this using its powerful infrared instruments, which can spot even the faintest stars and galaxies in space with impressive clarity. Unlike the Hubble telescope, James Webb's use of infrared lighting has exposed concealed parts of our universe, unraveling the mysteries of time and space one discovery at a time, and challenging the foundations of science. At the core of our understanding lies one theory: the Big Bang. It proposes that the universe began with a massive explosion some 13.7 billion years ago. While there are no photographs or videos to prove this explosion, the Big Bang theory has been widely accepted by the scientific community for years. Various observations and events in the cosmos seem to support this theory. For instance, the formation of planets and celestial bodies through supernovas or massive star explosions, which produce metals and planetary objects. This aligns with the idea that a colossal supernova-like explosion could have formed the cosmos as we know it. Another key piece of evidence for the Big Bang theory is the universe's expansion. Scientists believe it has been expanding since the Big Bang, and this expansion will continue until the universe can no longer hold itself together, ultimately leading to the end of time, space, and everything within it. For years, the Big Bang theory has been the cornerstone of cosmology. However, recent images from the James Webb Space Telescope have posed a challenge to this theory and the decades of scientific work built upon it. You might be wondering why this has caused such a stir. Well, the galaxies captured by the James Webb Telescope don't quite fit the expected patterns. When viewed through the lenses of the Big Bang and universal expansion theories, these images seem to defy our understanding. In simple terms, the new snapshots from the James Webb Telescope depict many ancient galaxies that appear smaller and smoother than anticipated. To grasp this better, consider the universe as an expanding balloon with galaxies, stars, and other celestial objects moving apart. As galaxies drift farther away, they should appear larger after reaching a certain critical point. Typically, the most distant galaxies are the oldest. However, it remains a mystery how the universe makes these ancient, far-off galaxies appear larger before our eyes. Scientists have found that dark energy and the universe's angular momentum play significant roles in this phenomenon. Esteemed experts have confirmed this curious aspect of the expanding universe, but the James Webb Telescope seems to challenge it entirely. The telescope's images show these ancient remote galaxies as being roughly the same size as those closer to us. This was entirely unexpected. What's more, the telescope has revealed galaxies that shine brighter and seem denser than our own Milky Way. They possess greater luminosity, mass, and significantly higher redshifts. Redshift, in this context, means that light from an object shifts toward the red part of the light spectrum. A greater redshift, like the ones observed by the telescope, indicates that these galaxies are moving away from us at higher speeds. It's important to note that this unconventional discovery isn't due to any issues with the James Webb Telescope or miscalculations by scientists. A similar finding was made when the Hubble Space Telescope images were analyzed back in 2014. showing that galaxies with redshift values of up to 5 displayed characteristics that seem normal in a non-expanding space. However, this knowledge was somewhat overlooked because there were no such findings before that time. Now, the James Webb Telescope has extensively confirmed this 2014 discovery. This trend continues for galaxies with redshifts as high as 12. Given the sheer number of galaxies observed by the James Webb Telescope displaying this pattern, it implies that the universe might not be expanding, and redshift could simply be a product of distance. This puts the long-standing Big Bang theory in a precarious position. If we want to reconcile the Big Bang theory and the concept of the expanding universe, it leads to a somewhat controversial conclusion. These ancient, distant galaxies must be extraordinarily small to counterbalance the optical illusion created by our expanding universe. To put it simply, if the James Webb Telescope showed these galaxies to be the size of a ball, in reality, they might be as small as a grain of sand, 100,000 light-year diameter. So could it be that these galaxies are just tiny? It's a possibility. However, the significant number of galaxies observed by the James Webb Telescope that follow this pattern suggests otherwise. The more we examine them, the shakier our confidence in the theory of an expanding universe becomes, and as a result, the Big Bang theory starts to lose ground. But it's not just the Big Bang theory at stake here. Our current scientific understanding suggests that the large galaxies we see today formed over billions of years through the merging of smaller galaxies. This makes sense, right? Well, here's the twist. When this merging process occurs, as we've seen in many cases, the supergalaxies formed usually exhibit odd shapes or distortions due to the intense process. However, the ancient galaxies revealed by the James Webb Telescope show no signs of cosmic distortions. It's as if nothing collided with them. Scientists expected these galaxies to show some evidence of damage or at least aging, but they appeared as smooth and well-defined spirals, similar to the newborn galaxies we see nearby. This poses a significant challenge to the galactic collision theory. Without signs of merging, it's hard to believe that these galaxies followed the process that we've long believed to be the formation of galaxies. Perhaps they didn't grow or collide at all, despite their age. The real mystery is still unfolding, but as scientists couldn't observe the optical illusion expected from our expanding universe, there's a growing sense of unease in the scientific community, particularly among Big Bang proponents. It appears that the universe might not be expanding after all. If this is the case, then maybe the Big Bang theory, which marks the beginning of time, never occurred. If the Big Bang theory is questioned, it forces us to rethink how time and the entire cosmos came into being. This is a significant paradigm shift that challenges our fundamental understanding of the universe, its origins, and even the concept of time itself. It raises questions about whether we have constructed the concept of time and used theories like the Big Bang to explain it. Roger Penrose described the James Webb Space Telescope as a kind of time machine, allowing us to peer billions of years into the past in the cosmos. However, if this same expert now suggests that we've been mistaken all along and time is not a valid concept, what does this mean for humanity? It implies that we may need to delve even deeper to unearth the actual truth about the origins of time. For those who are enthusiastic supporters of the Big Bang theory and are not ready to accept this recent discovery as a debunking, here are some additional facts to consider. Already, images from the James Webb Telescope have revealed stars that are over 14 billion years old, like the Methuselah star. We continue to discover more galaxies that don't appear ancient. In fact, there are over 100,000 times more galaxies in deep space with redshift values higher than what the cosmologists initially anticipated. It's implausible that so many large galaxies could form in such a brief time, at least not within the framework of the Big Bang theory. The real shocker is that recent research suggests the Big Bang theory has made 16 incorrect predictions, including errors in estimating the quantities of helium and lithium, as well as the density of matter in the universe. These cosmic contradictions paint an incomplete picture of our cosmic origins and cast doubt in the space-time theory's foundations. Our comprehension and interpretation of time have long been intertwined with the Big Bang, and now we must explore other solid theories to explain the notions of time and space. It might even be time to consider an entirely new theoretical standpoint, possibly with the assistance of the James Webb Telescope. Throughout the years, various discrepancies and theories have emerged in an effort to clarify the concept of time. Some theorists even propose that time, as we understand it, doesn't truly exist and is simply a human-made concept to help us distinguish the past from the present. Back then, such theories weren't taken seriously, but with the Big Bang Theory facing challenges, it may be necessary to revisit and reconsider these ideas, prompting a re-evaluation of the fundamental understanding of time and the universe. One intriguing theory suggests that time is but an illusion constructed from our human memories. Albert Einstein initially proposed this idea, stating, "The past, present, and future are only illusions, even if stubborn ones." According to this theory, everything that has occurred or will occur is unfolding right now. This theory might seem strange at first, but it gains merit when viewed from a different perspective. While we naturally perceive time as a forward flow encompassing past, present, and future, the laws of physics don't necessarily confirm or demand this precise pattern. From a physics standpoint, time could just as easily move backward or forward. This notion becomes more plausible when we consider the Big Crunch hypothesis. The Big Crunch hypothesis suggests that our ever-expanding universe will one day halt its expansion and begin to contract or shrink, akin to a reverse of the Big Bang. This raises questions about what transpires after the Big Crunch. A substantial portion of the scientific community posits that a new universe might emerge from a new Big Bang. Another group of scientists theorizes that our universe may reappear elsewhere. In this context, the latter theory aligns with Einstein's concept. In fact, there are even notions proposing that this cycle of our universe emerging elsewhere could repeat itself, giving rise to numerous universes. As bizarre as it may sound, it could be occurring right before our eyes. If everything happening now is also transpiring elsewhere, it might explain why those supposedly ancient galaxies mentioned earlier appear new, or why cosmologists frequently encounter peculiar interstellar objects in regions that would otherwise be empty. This perspective could suggest that the concept of past, present, and future is fundamentally different from what we traditionally perceive. Another unconventional theory portrays time as a human invention, contending that we live in a block universe where space and time are intricately linked. This concept is an extension of Einstein's theory of relativity, positing that all events, whether past, present, or future, exist within the four-dimensional space-time continuum. In simpler terms, this suggests that the future isn't something that's going to happen. It has already happened and is as real as the present. The only difference is that you won't experience that future until you reach its coordinates. Consequently, nothing fundamentally changes with time. In essence, everything that will ever transpire has already occurred. While it may appear peculiar, given the enigmatic nature of our universe, it wouldn't be surprising if this turned out to be the actual reality. A British physicist named Julian Barbour introduced another intriguing theory about time. His viewpoint suggests that our reality comprises a sequence of unique now moments akin to individual snapshots in our brains. Barbour postulated that our perception of the past arises solely from our brain's recollections. In other words, the concept of the past, in its entirety, doesn't exist independently. Barbour's theory also introduced the notion of a plutonia. According to him, each now moment exists within a plutonia, or a timeless landscape. Once again, this theory appears to be an extension of Einstein's ideas, prompting us to consider whether Einstein's theories may have been accurate all along. Albert Einstein's general theory of relativity transformed our understanding of gravity and space-time. He introduced the concept that massive objects like the Sun cause peculiar distortions in the four-dimensional fabric of space-time. The Earth orbits the Sun by following the curvature created by the Sun, and the force that keeps it within this curvature is what we interpret as gravitational pull. Einstein's theory provided a solid foundation for much of our current knowledge regarding time and space. While Einstein is no longer with us, his theory remains resilient, with no evidence yet able to disprove it. However, no theory is immune to potential inconsistencies or errors. As robust as Einstein's theory is, scientists and physicists continue to explore and expand its boundaries. Just as we recently discussed challenges to the Big Bang Theory, there may be unknown limitations or flaws in Einstein's concept of space-time. Through ongoing investigations, we may one day uncover the true nature of time, if it indeed exists. It's vital to recognize that science thrives on questioning both what we know and what remains uncharted, particularly what we think we know. Our progress in scientific understanding and technology has relied on a relentless pursuit of inquiry and discovery. Many of our most significant breakthroughs were born from challenging accepted beliefs. Consider how the Earth was once thought to be flat until new evidence demonstrated its true nature. Similarly, the prevailing view that the Earth was at the center of the solar system gave way to Nicholas Copernicus's revolutionary notion that the Earth is merely one of the many planets orbiting the Sun. The history of science is replete with such examples. Einstein's theory, while not without its potential imperfections, provides a foundational point for further exploration. However, it encounters a challenge in that it doesn't harmonize seamlessly with established principles and regulations of quantum physics. Quantum physics governs the behavior of the subatomic realm and has played a pivotal role in advancing technology and electronics. This has prompted scientists to embark on the quest to unify quantum mechanics with gravitational phenomena, hoping to attain a more comprehensive understanding of our universe and its origins. One theory that endeavors to bridge the realms of space-time and quantum physics is the loop quantum gravity theory. It proposes that space-time is composed of a network of loops. Nonetheless, this theory remains somewhat speculative due to the absence of the technology needed to substantiate it. Yet scientists persist in their efforts. Astronomers, for instance, have turned to intense flashes of light emanating from distant gamma-ray bursts in the pursuit of clues that might bolster the loop quantum gravity theory. These gamma-ray bursts result from the cataclysmic explosions of massive stars and exhibit unique spectral distortions that defy current scientific explanations. Perhaps by deciphering the cause of these distortions or tracing their origins, we could uncover insights to unravel the cosmic mysteries. To unlock the secrets of time and space, humanity may need to break free from well-established theories like the Big Bang and relativity. Some scientists suggest that quantum physics holds the key, while others, such as Robert Lee and George Hermannick, propose that space-time didn't evolve from the quantum world. This shift in perspective continues to undergo exploration and is expected to yield clearer answers in due course. Sir Roger Penrose's most intriguing and controversial idea is his belief that the Big Bang might not be the origin of our universe. This perspective challenges the prevailing consensus in cosmology, and it's worth delving into the rationale behind Penrose's compelling viewpoint. Penrose's skepticism about the Big Bang theory arises from a profound understanding of the universe's underlying principles and a desire to resolve some of its most perplexing questions. To appreciate his position, it's essential to grasp the conventional understanding of the Big Bang theory and its limitations. The Big Bang theory, widely accepted in cosmology, posits that the universe originated from a singular, ultra-dense, and hot point roughly 13.7 billion years ago. This event marked the beginning of our universe, with space and time emerging from this singularity. It has been the dominant model for explaining the expansion of the universe and the cosmic microwave background radiation, among other phenomena. However, the Big Bang theory encounters certain paradoxes and questions that have puzzled physicists for years. One of these is the singularity problem. The theory suggests that the universe began as an infinitely dense point, but this concept is fraught with mathematical and conceptual challenges. At such a singularity, the laws of physics, as we understand them, break down. Penrose has been a vocal critic of this aspect of the Big Bang theory. His alternative proposal, known as conformal cyclic cosmology, offers a fresh perspective.
Conformal cyclic cosmology, or CCC as I sometimes call it, is a cosmological scheme which I introduced in about 2005, sometime around then, which has, I talk about things which are called eons. Now our present eon would be starting with the Big Bang, the universe expands, and then it goes into this exponential expansion, which is fairly recently observed, and then that goes on forever. This remote expansion is physically equivalent to another Big Bang. And our Big Bang was the continuation of the remote future of an exponentially expanding previous eon. And the idea is these eons go on and on and on forever in both directions.
Conformal cyclic cosmology suggests that the universe undergoes an eternal cycle of cosmic births and deaths, each initiated by a Big Bang-like event. The idea is grounded in Penrose's belief that the universe, rather than beginning with a singularity, is instead part of an infinite cycle. In conformal cyclic cosmology, the universe we observe is just one phase of a sequence that includes previous universes that will be followed by future ones. Each cycle begins with a Big Bang, followed by expansion, evolution, and eventually a period of contraction. During the contraction phase, the universe continues to evolve, with galaxies, stars, and other cosmic structures gradually fading away. The process culminates in what Penrose terms Hawking points, named after the renowned physicist Stephen Hawking, in which matter is converted into photons and gravitons. One crucial aspect of conformal cyclic cosmology is the notion of conformal transformation. This transformation makes it possible to smooth out the boundary between the end of one cycle and the beginning of another, removing the singularity that plagues the conventional Big Bang theory. In this way, Penrose seeks to resolve the singularity problem and offer an alternative explanation for the cosmic microwave background radiation, suggesting that it results from the Hawking points of a previous universe. While Penrose's theory is mathematically consistent and addresses certain long-standing issues in cosmology, it has faced its share of skepticism and criticism. One notable critique concerns the question of observational evidence. Currently, there's no empirical confirmation of conformal cyclic cosmology, and it remains a theoretical construct. In contrast, the Big Bang theory is supported by extensive observational data, including the cosmic microwave background radiation and the distribution of galaxies in the universe. Penrose acknowledges the absence of definitive evidence for conformal cyclic cosmology, but emphasizes that it's a work in progress. He points to specific observations, such as the unexplained cold spots in the cosmic microwave background, as hints that his theory may offer valuable insights. He argues that as technology advances and our understanding of the cosmos deepens, conformal cyclic cosmology might gain empirical support. Another critical aspect of Penrose's perspective is the idea of entropy. In conformal cyclic cosmology, the second law of thermodynamics plays a significant role. This law states that entropy, or disorder, increases over time in a closed system. In the context of the universe, this implies that each cycle would have higher entropy than the previous one. Penrose contends that this aligns with the observed arrow of time, in which events consistently move from a state of lower entropy to higher entropy. Critics argue that the increase in entropy might not be sufficient to account for the universe's observed arrow of time, and further exploration is needed to fully substantiate this aspect of conformal cyclic cosmology. Sir Roger Penrose's belief that the Big Bang wasn't the origin of our universe challenges the prevailing cosmological consensus and invites us to question our fundamental understanding of the cosmos. His conformal cyclic cosmology offers an alternative perspective, addressing some of the perplexing issues associated with the Big Bang theory, such as the singularity problem. Now feel free to leave a comment to let us know your thoughts, and stay tuned for more of our videos.